Hello everybody, I'd like to look at the cubic function and how to sketch it. So the most general form of the cubic function is written as f of x is equal to ax cubed plus bx squared plus cx plus d, where a is not 0. Now because it's cubic, it has the highest power is 3, so there are 3 roots. 3 roots or 3 solutions. So 3 solutions to f of x equal to 0. Now if these roots are real, then that means there are 3 intercepts. So we'll be the x-intercept. So we'll be dealing with real values. So the challenge when we sketch these graphs is that before we even sketch anything, let's just try and reason things out a bit here. So if we have the y-axis and then the x-axis over here, and let's say we have now 3 roots, right? So we're gonna have maybe a root over there, let's call it R1, a root over there, let's call it R2, and a root over there, let's call it R3. So it's gonna cut this x-axis in 3 places. Now, let's assume as it cuts the first root, it's increasing, so it's going upward. In order for it to cut the second root, it would have to change direction and then start going downward. And then to cut the third root, it would have to change direction again and go upward again. So we would have something like this. So what this is telling us is that there are 2 situations or 2 occasions, 2 points where the function changes direction. And we call these the stationary points, or the turning point. So to sketch a cubic function, or cubic polynomial, we need to know a few things. So we need to get the 3 intercepts. So let's just say steps to sketch graph. So the steps to sketch would be, let's say, number 1, get x-intercept. I suppose get y-intercept. There's only one y-intercept, so might as well get the y-intercept. This one is normally much easier because you just set x to 0 and then just get whatever's left over. And then you need to get the 2 turning points, or the 2 stationary points. I'm saying get, maybe I should have said find rather, but I suppose it doesn't matter. Get, so I'm just going to say there are 3 here, 3 x-intercepts, there's 1 y-intercept, and then get stationary or turning points. I'm going to call it stationary points. And then there'll be 2 of these. Now we'll see why. We have to use some calculus here, but we'll see, we'll go through it, we'll get there eventually. So let's begin by getting the roots first. So let's start with number 1, let's get, let me just say find rather, find the roots or x-intercept. Now to find these x-intercepts, we need to solve for x where f of x is equal to 0. I suppose before we can even do this, we need an actual problem to solve. So let's use the one f of x is equal to x cubed minus 4x squared plus x plus 6. Now to factorize this polynomial, we need to first guess a root. So we're going to guess a root, or guess a solution. But obviously there's infinitely many values. We can't just start guessing and hope that we're going to guess the right value. So we need to look at this and see what looks like a reasonable value. So there's something known as the rational root test. It's just called rational root test. And what you do is, I do mention this in a different video, I'll put the link in the description there. A rational root test, it gives us shall we say, good candidates for guessing. So what we do is we take this value here, 6, and we take the leading coefficient here, which is 1, which imagine there was 1 there, and we basically say we consider all factors of 6 over 1 and plus or minus. So it would be a set of values like 1, -1, 2, -2, 3, -3, and 6, -6. So we're hoping that one of these will give us a solution. So let's start, I suppose, with 1. Let's try 1. So let's try 1. So let's try x is equal to 1. So f of 1 is equal to what? So it's 1 cubed minus 4 times 1 squared plus 1 plus 6. This is equal to 1 minus 4 plus 1 plus 6. And what is this equal to? Well, 1 minus 4 is minus 3. Minus 3 plus 1 is minus 2, and minus 2 plus 6 is 4. This is not equal to 0, so therefore 1 is not a root or a solution. Now let's try x is -1. So let's try. So this is a bit tedious, but you know, what are we going to do? So let's try -1. So f of -1 would be -1 cubed minus 4 times -1 squared plus -1 plus 6. Now let's see what we get here. So -1 cubed is -1. -4 times 1, so -1 squared is +1, so -4 times +1 is -4, plus -1 is just -1 plus 6, and I think here we have ourselves a solution. -1 minus 4 is -5, -5 minus 1 is -6, -6 plus 6 is 0. So now we are very happy, because this means -1 is a root. So that means, so if x is equal to -1 is a solution or a root, this implies that x plus 1 is a factor. So this is a factor of f of x. So what this means is that we can write f of x as x plus 1 times some quadratic. And this will be a quadratic, so this will be something like ax squared plus bx plus c. How are we going to find this quadratic? We have to do some form of division. So I have a separate video where I'll talk about all that. There's different methods you can use, long division and so on. I'm going to just use long division, so let's just use polynomial long division. But there are other methods like synthetic division, and you can even just use inspection. Some people use inspection because it can sometimes be quick. So let's just do polynomial long division. I should have written long division. So we know x plus 1 is a factor, so we can write x plus 1 here, and then we're going to divide our actual polynomial here, which is x cubed minus 4x squared plus x plus 6. So x goes into x cubed x squared times, then we take this x squared and multiply it by the factor. So x squared times x is x cubed, x squared times plus 1 is plus x squared. Now we do subtraction. So the x cubed minus x cubed is just 0. The negative 4x squared minus x squared is negative 5x squared. And now we must bring down this other term, which is plus x. X goes into negative 5x squared. Negative 5 x times negative 5x times this factor gives us negative 5x squared minus 5x, and then we're going to subtract this. So the negative 5x squared minus negative 5x squared is just 0. Positive 1x minus 5x is positive 6x. Now we bring down that term, we end up with 6x plus 6. Then we ask ourselves, okay, x goes into 6x how many times? Positive 6 times. Positive 6 times x plus 1 gives us positive 6x plus 6. We subtract this, we get 0. So we are happy because now there's no remainder at least. That's very good. So this is just 0, so there's no remainder. So now what this means is this person, this guy on the top here, is our quadratic. So f of x can be written as x plus 1 times that quadratic over there, which is x squared minus 5x plus 6. So we're not done yet, because now we want to further factorize our quadratic over here. So let's see if we can do that. Well, if we do that, x squared minus 5x plus 6 is equal to what? Well, 6, the factors of 6 are 1 times 6 and 2 times 3, I suppose. But we have a negative 5 over here. So we need values that will add up to negative 5. So how about 6? This is positive 6. Positive 6 can be negative 3 times negative 2. Because if you add negative 3 to negative 2, you get negative 5. So these numbers will be used in our factorization. So x squared minus 5x plus 6 can be written as x times x like this, and then we can put these values here, negative 3 and negative 2. So all in all, f of x can be written as x plus 1. This was the factor we guessed above earlier, and then through our long division, x minus 3 times x minus 2. And now in this form, to get the roots, we say f of x is equal to 0, and this implies what? That x plus 1 times x minus 3 times x minus 2 is equal to 0. So our roots are negative 1, positive 3, and positive 2. So the x-axis will be cut at those three positions. So on the Cartesian plane, the x-axis will be cut at negative 1, positive 2, and positive 3. But we're still not done, so let's get the y-intercept. Well, to get the y-intercept, we must set x is equal to 0. So we just calculate f of 0. And f of 0 is 0 cubed minus 4 times 0 squared plus 0 plus 6, and this is just 6. So the y-intercept, okay, it's not drawn to scale, but it will be here. There will be a 6 here, and it will cut here. So we know where the graph is going to ultimately cut the axes, but we don't know where they turn, where the graph turns, the turning point of the graph. So now this is where things get a little bit more challenging. We have to use some calculus, and we need to get the stationary points. I'm going to say find stationary points. And to get the stationary points, we need to get the derivative of the function. So find stationary points. So here's a function f of x, which is x cubed minus 4x squared plus x plus 6. Now the first derivative, f prime, and I do have a video of this where they explain about derivatives, so it's 3x squared minus 8x plus 1. We need to solve for x, where f prime of x is equal to 0. Now if you see, the derivative is always 1 degree lower than the original function. So we had a cubic function, so the derivative is quadratic. This is quadratic. So there are two turning points, or two stationary points. So if f prime of x is equal to 0, this means 3x squared minus 8x plus 1 is 0. This cannot be factorized simply, so we're going to have to use the quadratic formula, which is x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. In our little example there, the a is 3, the b is negative 8, and c is 1. So we can solve here. So x is negative 8 plus or minus the square root of negative 8 squared minus 4 times a is 3, and 1, c is 1, and this is all over 2 times a, which is 3. And if we do this, so obviously negative times negative is positive, so we have positive 8 plus or minus the square root. Negative 8 squared is 64 minus 12, and this is all over 6. Now we can further factorize here, so we can get 8 plus or minus 64 minus 12 is the square root of 52 over 6. I suppose you can factorize this further, but you might as well just go straight to the calculator and let's see what the values are. So we're going to get two solutions, one where we take the plus and one where we take the minus. So let's just call it x1. So x1 will be 8 plus square root of 52 over 6. And then let's make x2 the one with the minus. x2 is 8 minus square root of 52 all over 6. Now we're going to have to round off to maybe let's say 2 decimal places. So I'm making it approximately equal because we do lose accuracy with rounding off. So for x1 we get 2.54, and for x2 we get 0.13. Now these are just x values, so we want to get the corresponding y values. So let's get y1, which is f of x1, which is f of 2.54. And if we plug this into our original function, please note here we are plugging it into the original function, not the derivative. So this is just 2.54 cubed minus 4 times 2.54 squared plus 2.54 plus 6. And then with y2, it will be obviously f of x2, which is f of 0.13. And then similarly, we just, again, of course, we're going to have to use calculator here, so 0.13 cubed minus 4 times 0.13 squared plus 0.13 plus 6. And using a calculator, we can just write y1 is equal to, I'll say again approximately, because like I said, we do lose precision, is negative 0.88, and y2 is 6.06, like I said, approximately. So these are points, these are the stationary points, so we want to write them as actual points. So we have more information now. Again, just a rough sketch here. We already have our roots. We knew our roots was -1, 2, and 3. And we knew our y-intercept was 6. Now we've got additional information. We know one of the turning points are where x is 2.54, which is probably in the middle here somewhere, and -0.9. So it's somewhere, maybe, let's say, there. So that point is the 2.54 and -0.88. And then the other one is where x is 0.13, which is very close to the origin here, and just above the y-axis, intercept, sorry, so it's somewhere there. And again, if we just put an arrow, I can even just extend it there. So already we can see our function is going to probably go something like this. But there's a little bit more. We can speak about second derivatives and to see where we're getting a maximum or minimum. So we can see just from plotting that this turning point, or that stationary point, this one here, is a what we'll call a local maximum, because that's when the graph is at its highest. And this turning point over here we can call a local minimum. But we can actually calculate or determine this from using calculus as well. So what we do is we take our first derivative, the derivative there, which is if I rewrite the derivative, it was f prime of x, which is 3x squared minus 8x plus 1. So the second derivative, so this is the derivative of the derivative, will be 6x minus 8. Now for some value, let's say for some value c, for some value c, if the second derivative of the function taken at the point c, if it's greater than 0, then we have a local minimum. And if it's less than 0, we have a local maximum. Now we could see the minimum and maximum just by looking at that graph. So these are our stationary points, and let's see what we get if we take the second derivative, f prime, at the various x points. So 2.54, 6x, so this will be 6 times 2.54 minus 8. We don't even have to calculate this. I mean, 6 times 2.5 is definitely more than 8, so this is greater than 0. So this means it's a local minimum. And then for the other one, let's use 0.13. Here we'll get 6 times 0.13. Now this is going to be a small number, minus 8. So this is going to be less than 0, and this is going to be a local maximum. And if we go, let's actually re-sketch the graph just to be more, maybe bigger now and better. So the x-intercepts were -1, 2, and 3. The y-intercept was at 6. So we know our graph goes through there. And then the stationary points, 2.54 and -0.8, so that's about here. And we did predict that this would be a local minimum. see it here, it's a local minimum. And then the other stationary point, which is 0.13, that's the x value, and then the y value is 6.06, so it's about there. And we didn't know, we can see here from the calculus that this is a local maximum. So our graph will go like this. It must go through the y-axis, it must turn at the stationary point, then it starts going down till the next turning point or stationary point, then it goes up again. And you can extend it a bit if you want. So you end up with something like that. Now this is quite tedious and it takes long, and we can even go further and speak about what happens when the second derivative is 0. This is known as a point of inflection, but I'm not going to cover that here. We just wanted to go through the basic sketching of a cubic graph. Alright, that's it for this video. Thanks, bye bye.